So this lesson is going to be how electromagnetic radiation interacts with electrons and atoms. Now, in the previous lesson on electromagnetic radiation, if you have never studied any physics, you might have been a bit confused and thought, how is this chemistry? Well, this lesson is going to make it clear why we need to know about electromagnetic radiation when it comes to electrons and atoms. So why electromagnetic radiation and chemistry go together. Now, what we have here is a diagram representing an atom. We've got the nucleus right at the centre, and then what we've got here are our energy levels, or our energy shells. Electron shells might have been called in the past. We'll call them energy levels. And each one of these gets a number that's called n. So we've got n equals 1, 2, 3, 4, and 5. And as you get out, you can see that the shells get bigger, but the distance between shells gets smaller. And we have got one electron in our first energy level in this diagram. Now, we know from the previous lesson on electromagnetic radiation that every wave with a particular wavelength or a particular frequency has an exact amount of energy. And these are energy levels. So in order for an electron to move between these energy levels, it must gain enough energy to get here. Now, if this electron doesn't gain the full amount of energy, say if this electron gains enough energy to go here, well, there's not an energy level there, so it doesn't move. It'll stay here. If it gets enough energy to go here and further, well, it's not going to travel anywhere because it's making a transition into nothing. So it won't move. Only if it gets exactly the right amount of energy to go to here, or here, or here, or here, to each energy level, will it move. So there are very exact wavelengths or frequencies of light that an atom can absorb and use that energy to move an electron from one energy level to the next. So we'll draw an illustration of that. So if we've got a beam of light travelling in and it hits this electron, that has energy which is equal to hf. And if that energy is the same as the energy needed to go from n equals 1 to n equals 2, the electron will move up that way. If the energy is enough to go to n equals 3, it'll move to here, to n equals 4, the next one, n equals 5, the final one. And if it actually has enough energy to break free of all the energy levels, then the electron will completely leave. And that's what we would call the ionization energy, is if there's enough energy for it to get just beyond the final shell, it will completely leave and we'll have ionization. In this example, we're going to say that it gives it enough energy to go to the n plus 4. So that energy was enough to move that electron from there to here. And that energy difference, so that delta E, that's also equal to hf. So whatever energy goes in, energy has to be the difference here. They have to be the same. And so if a wave absorbed, the electron gains energy. And we can talk about it becoming excited. So that would be an electron in an excited state. This state, and it's where it starts, we would call that the ground state. Now this energy here needed You constantly need that energy provided in order for that to stay in that position. If you turned off this light source and left the electron here, so we'll just draw it again here. If we've got the electron now still in n equals 4 here, and we leave it and it's got no energy, electrons are going to want to get close to the nucleus. It's negatively charged, the nucleus is positively charged. It's going to want to move. And it can drop down energy levels. It can lose energy. And it can go from 4 to 3, it can go from 4 to 2, or it can go from 4 to 1. Just because it's losing energy doesn't mean it always has to go to n equals 1. It can go less. So what we're going to do is we're going to represent it falling this time down to n equals 2. So not the whole way. And when it does that, it will move here, and it's lost energy, and we know from the first rule of thermodynamics, energy can't be created or destroyed, so there's no such thing as losing energy. The energy that's lost from this electron is transformed into a wave of light. So as it does that, it gives off a photon. Now this delta E, which equals HF, is going to give a wave of energy HF. And now this wavelength and this wavelength are going to be different because that energy is different. This energy is bigger than this one. So the frequency is going to be smaller here, bigger here and smaller here. And this is why electromagnetic radiation is really important in atoms, because electromagnetic radiation can be used to move electrons around. And we know that most chemistry is to do with electrons moving. And so if we can use electromagnetic radiation to move electrons, it means that we can give chemicals different properties, get them to react, get them to give off light, whenever we expose them to electromagnetic radiation. So if a wave is absorbed, the electron gains energy and it becomes excited. If an electron loses energy, we say that a wave is emitted. Double T. So if an electron loses energy, we have emitted radiation. If an electron gains energy, it has absorbed radiation. Now, whenever we excite electrons, they're usually starting in their ground state. Whenever we are losing energy, they don't have to return to the ground state. They can return to any of the other energy shells. And so what you would notice is that this specific wavelength allowed it to go from n equals 1 to n equals 4. A different amount of energy would be needed to take it from n equals 1 to n equals 2, or, again, n equals 1 to n equals 3. And so each atom will have a set number of wavelengths that it can absorb to allow its electrons to move. And every atom, because it's got a different charged nucleus, the energy levels are going to be different for each type of atom. So the amount of radiation that can be absorbed, the wavelengths. And remember, every transition up is going to be matched by a transition down. So we can look at an atom and see what wavelengths it absorbs or what wavelengths it emits. And that can tell us about these energy levels. And every atom is going to have different values. And we can compare the wavelengths that are absorbed, the wavelengths that are emitted between elements, and use that as a way of working out what the element is and what values the different energy levels have relative to one another. We can use that to identify an atom. Now, how might we do that? Well, what we do is we use a prism. Now we shine some white light, sorry, there is yellow here, it's not very easy to see, but we shine white light through a prism and it spreads it out. So we have white light like this, and the process of refraction separates it out into this full spectrum. So that's a prism. Now if we have nothing and it's just pure white light, what we get is the full spectrum. So what we have is red, orange, yellow, green, blue, indigo, violet, light, all the colours of the rainbow. But what happens if instead of pure white light, if we interrupt this process and we put a box here which contains gas of an element? So it's usually gas, and you can make gases out of all the elements. So this can be metals, this can be a natural gas, but we want atoms of the gas. Pass that through. What happens is that the gas is going to absorb some of the wavelengths of light. The rest of the light will pass through the prism, and we'll get a spectrum, but there'll be some lines missing. And what we get there is an absorption spectrum. So this time we see all the colours, but there are some lines missing, and those are the lines that have been absorbed by the sample. Let's move that up. That's been lost by the sample. Now we can modify this again, still using a prism to separate out the light, but this time what we do is we have our sample and we give it energy through heating it. And then it gives off light, which we pass through a prism. Now this light, we use heat. This excites the atoms, excites the electrons, and they move up to higher energy levels. And then they're going to start falling back down. And so we're going to see the light that gets emitted. So this is going to be emitted light. So it's not going to be white light anymore. It's going to be emitted light. And we're only going to have a very few number of wavelengths corresponding to the transitions that can happen from higher energy levels to lower energy levels within an atom. And when we do that, we get an emission spectrum. And an emission spectrum has mostly black, where we're not seeing anything, but then we have specific colours that we see, and that corresponds to a wavelength of light that has been emitted. Now if we look very closely at the lines, you will see that the lines in the absorption spectrum that are missing are equal to the lines in the emission spectrum that we see. And that's because that line, say if that was an electron going from n equals 1 to n equals 2, that line is absorbed by the sample to allow that transition upwards. But when we've excited the sample and it's de-exciting, that amount of energy is released. So whatever lines an atom absorbs are the same lines, the same wavelengths that it can emit after it's been excited. So those two spectrum, if you add them together, gives you just a continuous spectrum. And every type of atom will have a different set of values. And you can be asked from a diagram like this, or a table of different wavelengths, you can be told how to work out the energy associated with that. So just using E equals HF. And remember, absorption is electrons going up, emission is electrons going down. Now in this diagram we had here of heating our sample and then letting it emit light. This part here is the basis of flame tests. So when you do a flame test on a metal, you heat up the metal and you're actually able to see the colour. The colour that you're seeing, and the reason why you see colour, is because you heat the sample, the electrons in each atom get excited up, then they fall back down to different energy levels, and they emit particular colours, and you can use those colours to identify what that is. Now, there is a table, a whole page in the data booklet dedicated to this, and they can ask you questions about it. So I'll see if I can get that a bit closer. It's page 15 in the data booklet. And what we have, we'll start at the bottom. We've got the flame colours. So these are our flame tests. They tell you the colour, but they also give you a wavelength. So you can be asked in advanced higher not only for the colour that an element gives, but the energy associated with that colour, because you can use the wavelength and the equation E equals hc over lambda to use that wavelength to turn that into an energy. Now, in the metal vapour ones, the table above, that's where a metal has been turned into a gas and light has been shone through it. And these would be the lines that are absorbed. Again, you could be asked to turn these wavelengths into energy values. Now, the top is particularly interesting. This says it's gas discharge lamps, but it gives us hydrogen and helium. We'll talk about the Balmer series later on. But we've got hydrogen and helium. Now, what is important about these is that hydrogen and helium are the two elements that make up the sun. So how these lines were first discovered is actually if you take light from the sun and pass it through a spectrum, you get something like this with some lines missing. And that seems really confusing because we think about the sun as being the source of all light. But it's not, because the atmosphere of the sun is made up of hydrogen and helium. And those atoms absorb some of the light that is produced. So the hydrogen absorbs all these different wavelengths, the helium absorbs these wavelengths. And so you could get asked a question about sunlight, and you need to remember the sun is made of hydrogen and helium. So they absorb and remove some of these wavelengths from natural sunlight. And so you could get a diagram and be asked either to identify which bands are from helium, which ones are from hydrogen, or be asked to calculate energies. Now, this Balmer series, we're going to discuss that because it's not the only series that exists for hydrogen. So hydrogen has only one electron. Hydrogen has one electron. And we're just, instead of drawing an atom, we're just going to draw straight lines to represent the different energy levels. I should start from the top. So something like that represents them. I apologize. But we'll have n equals 1, n equals 2, n equals 3, n equals 4, 5, and n equals 6. And definitely what you notice is that the energy levels keep getting closer to one another. Getting closer to one another. Now, hydrogen only has one electron. And that's usually going to start here. And if it goes up to, say, we have a beam of light coming in, and it's allowed that electron to go up to n equals 6. Now n equals 6 is not the final level, it's just the one that I've drawn there. It goes to there. Now, that electron, when it goes to its excited, it can do this. It can go back to n equals 1. Or it can go to n equals 2. Or it can go to n equals 3. Now you can see that if it's going to n equals 1, it's going to be a lot more energy than if it goes to n equals 2, or if it goes to n equals 3. And again, if it's going to n equals 3, that's a lot less energy than going to n equals 2. And all the bands that exist beyond this have these options. They can always fall to different energy levels. The biggest energy is always going to correspond to falling to n equals 1. And for hydrogen, the series of lines that gets produced whenever they fall to n equals 1 is called the Lyman series. And the Lyman series, all of the wavelengths fall in the UV region. If the electrons fall to n equals 2, that's the Balmer series. And the Balmer series, most of them fall in visible. And then this final one, which we don't really learn about, is the Paschen series, which is falling to n equals 3. Paschen, P-A-S-C-H-E-N, and that is in the infrared region. So you can see this is higher energy, medium energy, and then lower energy. And you'll get a whole series of bands corresponding to that. The Balmer series is the ones that will be missing from visible light. So that's why that's given in the data booklet for hydrogen, the Balmer series. Now, if you are asked in an exam to look at the Balmer series and that you've got some values that have higher energy than that, the reason why they have higher energy is because they'll have fallen to a lower energy level. Balmer series is n equals 2. Anything that has more energy will have fallen to n equals 1. Anything with less energy will have fallen to n equals 3, 4, or 5. Now, another thing to note from this is that obviously these lines keep getting closer and closer together. And eventually they get so close at a point we call n equals infinity. At n equals infinity, rather than seeing individual lines, you start to see a band. So a thicker band of lines, which we call a continuum. A continuum is just a small version of a spectrum. So if this is a full spectrum, a continuum might be between those two regions. That's a continuum. And so you'd have had all these lines here, individual lines, and then a continuum of all those colours together. Where you see that continuum, that's where you've gotten to the point where the different energy levels are so close to one another you can't tell them apart. And once you reach the final n equals infinity, you're not going to see anything above that, because after that we've had ionization. So any energy above getting to n equals infinity is ionization energy. And ionization energy is going from the ground state, n equals 1, to there. And that's what you've got to remember. Ionization is n equals 1 to here. And so last year in higher, when you looked at ionization energy, you needed to know the trend. Now you might get asked to turn the ionization energy into a wavelength. And so you also have to use the data booklet looking for your ionization energies. So this time it's on page 11. On page 11, your first ionization energy in kilojoules per mole, you can be asked what wavelength of light is needed in order to promote an electron to ionization. And in that, if you're going to do that for ionization energy is equal to LHC over lambda. So if you're working it out for lambda, lambda is equal to LHC divided by the ionization energy. Now remember that H, that's in joules, is in joules. Ionization energy is in kilojoules. So you need to get those into the same value. So for this one, you would multiply this by 1,000. And that turns it into joules, if you want to use that equation. Okay? So ionization energy is LHC over lambda. The ionization energies are given to you in the data booklet on page 11. And you can work out the wavelength using this equation. But remember that if one value is in kilojoules and the other value is in joules, you need to do that relationship of turning kilojoules into joules by multiplying by 1,000. So that hopefully illustrates why electromagnetic radiation is important in chemistry, and why that was the first thing we made you do, is work out the energy. Electrons can move between the different energy levels, or what we used to call electron shells. Each wavelength of light that can be absorbed corresponds to the energy difference between two energy levels. And what that does is takes an electron from the ground state to an excited state. Any excited electron can fall back down to a lower energy level. It doesn't have to be the ground state. And every time an electron falls down from one higher energy level to a lower one, it gives off a photon. It gives off energy in the form of a wave. And you can use the energy or the frequency or the wavelength of that light to work out the energy difference between energy levels within a given atom. This can also be used to identify specific atoms, because each atom will have a different number and wavelength of light that can be used in order to promote its different energy levels. And the reason each atom has a different set of energy levels is because they have different nuclei and different numbers of electrons, which change the energy levels. If we are doing this in an experiment, you can either look at the absorption, so that is the light that is absorbed by the atom, or the light that is emitted. And absorption and emission spectra are opposites of one another. So where you see no light being absorbed in an absorption spectra is where you will see light being emitted on the spectrum. And these bands can be used to identify particular atoms. When it comes to atoms like hydrogen, every single time that an electron can fall, it can fall to a different energy level. The further it falls, the more energy it releases. And so for a hydrogen atom, when electrons fall to the ground state, n equals 1, we get UV light emitted. When it falls to n equals 2, we get visible light emitted. And the most dominant lines in this are in the data booklet on page 15. And if it falls to n equals 3, we get even less energy, that's infrared. The lines, the energy levels, get much, much closer to each other as they get further out. And eventually you reach a point where they're almost overlapping. And instead of a single band in the absorption or emission spectrum, you see a continuum. which is a band where we see part of the spectrum in full. And the energy needed to take an electron from the ground state to n equals infinity is the ionization energy. And you can work out ionization energy from a wavelength. If you're told this wavelength ionized a sample, what is the ionization energy? Or you could try and find out what wavelength of light is needed to ionize an atom from the first ionization energy on page 11 using this equation. So I hope that made clear why electromagnetic radiation and atoms, and chemistry are studied together, and why it's really important, and how it actually allowed us to understand atoms a lot better. So that was our second lesson on electromagnetic radiation and atoms, and thank you for your attention.